is the figure from the paper, okay, and what, so the title of the paper is Attention is All You Need, okay, and can you hear me? ये चल रहा है ना? Okay, हाँ. So this is the title of the paper and this is the architecture we are doing. So let me just show you this one, okay, and some parts of it we have completed. So we are doing multi-head attention. We'll of course talk about what is add and normalize, what are all these things doing. So this is one block, and then you in this paper they use 6 such blocks, okay. And then finally you see in the end whatever we are doing to compute a softmax over our vocabulary, okay. So I'll keep this aside, let us go and okay. So this is what we were doing. Right. So we were talking about this equation last time. Let us start from here. So we were talking about this equation last time, and let me just put the date. It is 29. So what is this equation doing now? So right now we said we will not talk about this decay for the time being. What is Q? So let us keep these two things together. Q is your, so there is one change, I mean not one change, just one information. So original transformer paper, it did not keep 512 x12, I mean not 512 inputs, rather it had the input size was the maximum or the longest sentence, okay. Now we can simply say that we are talking about a case in which maximum length is 512, so that does not change anything for us. Now we were doing Q into KT. What is Q? What are the dimensions of matrix Q? So this is 512 cross 64. Why 512? Why 512? Because we are assuming that we are taking 512 inputs, 512 words as an input at one time, okay. So 512 inputs. So this is basically 512 rows and 64 columns, because each Q is 64 dimensional. Now Q is same, but those are K vectors, sorry, K is same, but difference is that those are K vectors now instead of Q. How do you compute K? So how you compute K is simple. You have Wk and then you multiply it with Xi's, okay. Okay, so you again get what are the dimensions of K itself? 512 cross 64, but then you want to take dot product, so you have to take the transpose, that gives you 64 cross 512, and what is this resultant thing? Yes, we were here. 512 cross 512, and what will this actually give me? So this number times this number gives me one number. What is that? The dot product between query 1 and key 1. So that comes here, Q1 dot so this is actually K1 transpose, right? All these are K1 transpose. So this is transpose, transpose, and so on. Okay. So this is my K1 transpose, and by now you know our notations are messed up. Okay. So this one, what will be the next element here? Q1 dot K2 transpose, and then all the way until Q1 dot K 512. Okay. What is this whole row? What is this row? We have done everything before. We are just doing it in matrix form. That's it. What is this thing? What was the name? Attention. Attention scores for first word, first output. Now, what are you supposed to do with this? Take softmax of this. So, precisely that is what we are doing. You are doing Q cross KT, that gives you this 512 cross 512. You take softmax, but now let us bring this thing into picture. So, they say you have to divide it by under root of dk, where dk is nothing but the dimensionality of your these vectors, which is 64. Okay. So, dk is 64 because these vectors, they are of size 64. And the paper says, so what will happen if you multiply these things? When you will back propagate, your numbers will be a bit larger. So, by dividing some number, you are basically keeping them numbers low. So, this helps during back propagation to keep your gradients in a good range. Now, what is this whole thing, resulting thing? 512 cross 512. Everybody is with me until now? 512 cross 512. Now, what is this guy? So, let us do something here. What is that now? Oh, okay, let me try to do it in a. So, this whole thing is. So, we have this 512 cross 512, that is coming from Q cross KT divided by under root of dk, and then do softmax of it. So, all these rows, they are summing to 1, and every element is between 0 to 1. Okay. So, this is what it is. Now, so these are my attention distribution, right? These are my attention distributions. So, these are 512 in row, 512 in column. Now, what do I do with this next? So, what are the size of vector V? 512 cross 64, right? So, this is 512 cross 64, and 512 cross 64, that means your V1 is like this, V2 is like this, and there are 512 in total. So, this is what you have. And now, this is going to give me what? A matrix of size 512 cross 64? Yes. So, 512. Cross 64. What is this final output? So, this is our softmax. We have multiplied softmax with value. So, this is my final output. Now, what is this guy, what is this guy, and so on. What is each row out there? So it is alpha 1 V1 plus alpha 2 V2 plus alpha 3 and all the way until alpha 512 V 512. This is your output of the whole attention process. Okay. Now, so just one vector of size 64. This is 512 cross 64. So if we want to draw this again, somewhere here, right? This is the 64 we are talking about. So whatever just one thing I talked about, it is this 64. But then the same matrix is containing how many numbers? How many rows? 5 and 2. So you are basically talking about V1 and here, so that equivalent thing you will get, am I right? Yes, yes. So this is V2 and all the way until V512. Okay with this? No? How many of you are okay with this? How many want me to repeat something? This part is fine, I think. Okay? You multiply it with V. What are the dimensions of V? So 512 cross 64. That means this V matrix is containing all the values, all the value vectors from position 1 to position 514. Okay? Now this is done. This just multiplication of first row with this whole matrix is going to give me what? See, this one gets multiplied with this, okay? This one will get multiplied with this, so wait. So you say this should be transposed? No, this thing should be transposed. Wait, let me think. So V is this. We are saying our rows are softmax, right? So this thing will be multiplied with. So what we have here is alpha 1, alpha 2, and actually this should have been alpha 11, alpha 11, alpha 12, alpha 13, all the way until alpha 1, 5 and 2. Now alpha 11 should multiply with V1. So let us talk about just this vector. Forget the whole matrix, just this vector. This one gets multiplied with this, then this one gets multiplied with this one. But isn't this fine? right? हाँ
सर ये ऐसा होना चाहिए जो v वाली मैट्रिक्स है इसको ट्रांसपोज करके इस तरफ से मल्टीप्लाई करना चाहिए और उसको इस तरफ शायद
नहीं सी see, so what will this give me? Alpha 1 1 times, so let me just call alpha 1 alpha 2 because I am just talking about one vector. So this is alpha 1 times v1
सर जो v1 है अपना मैट्रिक्स के अंदर इसको अगर अपन एलिमेंट्स के अंदर तोड़ के लिखें तो शायद हमें
see this is 1 cross 5 1 2, this is 5 1 2 cross 64, this should give me 1 cross 64, that should be my output of the first value. So is it not that? No, see what transpose will do is that these guys may not sum to 1. So basically these two matrices are not the same. One either row or column is necessarily summing to 1, the others you have no constraints apart from the fact that they are all less than, I mean between 0 to 1. So guys, I am doing matrix multiplication wrong, that is it. There is no big thing here. So alpha 1 gets multiplied with the first one.
इस तरीके से देख सकते हैं कि 512 वर्ड के अगेंस्ट हमारे पास अटेंशन स्कोर है अब उस स्कोर को मतलब हर वर्ड को कितना अटेंशन देंगे अपन इसलिए 512 से मल्टीप्लाई करेंगे मतलब फर्स्ट वर्ड
No, see, intuitively this makes sense to me, but what we are doing is not giving me that calculation that we are looking for. So this one should ideally multiply with the, so what we are looking for is alpha 1 times v1. Now this is a scalar, but this is a vector.
सर अपन उसके अंदर तो ये करते थे ना एलिमेंट वाइज नहीं सर जब अपन ए निकालते थे तो स्केलर को वेक्टर से मल्टीप्लाई करते थे तो इसमें स्केलर अपना अल्फा 1 1 है
Right,
और वेक्टर है वो v1 है
right.
तो सर इसके अंदर अपन अगर जो एलिमेंट्स हैं दूसरी मैट्रिक्स के जो बी मैट्रिक्स लेते हैं अगर अपन उसके एलिमेंट्स को वेक्टर ही मान के चलाएं और सर 5 1 2 क्रॉस 1 लें तो ये हो जाएगा
See, I'm convinced this is right, but right now I am confused. And I don't think it should have been that complicated to figure us out. So alpha 1 is going to get multiplied with all of it, that is evident, and this is what we want. My problem is, are we getting this thing? No, we are getting the, no, see, this is right, this is right. See, alpha 1 gets multiplied with the first element, so let us try to fill these things out. मतलब तुम लोग मेरी हेल्प नहीं करोगे और चाहोगे कि कोर्स पास कर जाओगे ना. So alpha 1, let me call this v1 1. So alpha 1 1, I will need more board space. So this is alpha 1 1. Can I simply call it alpha 1? Yes. So alpha 1 v1 1 plus I will get alpha 1 2, guys, alpha 1 2, sorry, alpha 2, and this guy comes from v2 but is the first element, and this way I go all the way until alpha 5 1 2 and v 5 5, 1, 2, but first part. Okay. Now this is what? So basically what I have just filled up is this position of my output vector, right? Now what will the second multiplication give me? Here. This was 1 cross 52.
1 cross 5 and 2 and 5 and 2 cross 64, so 1 cross 64. So the row vector column.
Okay, right. So what we will have is a row. Right, so what we will have is a row. So this will give me the first element. First element is done. So this one, and then second multiplication, the second multiplication is going to give me the second element, right? So this gives me first element, and now the second such equation basically will give us, and this whole thing will be 1 cross 64, this is V1 64. This one? I just want to represent every element is coming from my vector 1. See, in the end what you are computing is this, which is vector V1. So I am just saying vector V1's first element, vector V1's second element, and so on. No, yes, but here they were. No, output of self attention. Okay. So this one? I am saying whatever I am going to do this one, I am going to do the same for rest. Okay. Right. So right now we are saying through this calculation I am getting just one vector. Now with this 5 and 2 you will get 5 and 2 cross 64. Right. So now this makes sense, everything was right. Okay. So this is going to give us, now, so again I'll have to go up. What have you ended up computing? This was V2. No, what was this? So this second element is just V2 all the way until V5 and 2. Okay. So thank you for all this. Now what do we do next? We have computed self attention V1. What are we still missing in what we have done already? Yes. What are we still missing in what we have done already? See, we have computed just 64. We have computed just first 64, but output is supposed to be 5 and 12 dimensions. Okay. So how many heads we talked about? 8 heads. Now this was coming from the just one head. you do all these computations in parallel for other heads. Okay. So, in parallel compute V's of 8 heads. Make sense? I don't need to do any calculations here, right? Now, in those heads, WQ, WK and WV, are they going to be same as this or different? So, you need to write this down that they are all different. So, 8 heads, they are computing different parameter matrices, different parameter weights, and they happen to be of the same dimension, but weights are not shared, weights are different. Okay. So, we are done with this multi-head thing as well. Now, yes, in this whole computation, so if you remember deep learning, neural networks, what was every layer doing? So wait, let me go to, yes, we were here. Output. 512. See, one was 64 from one head. Now you have 8 such heads. So 64 cross 8, that gives you 512. This one thing is 512 dimensional. Okay, this is 512, this guy is 512 all the way until here, this is 512. Now we understand, we have talked about every damn thing about this layer. Is that okay? And this is one of the core concepts that basically makes transformers different from RNNs, parallelizable and so powerful. एक बात बताओ, so can you do this all 8 head computation in parallel? Or there is dependency among them? So can you parallelize the computation of all 8 heads? You can. Okay. Now, what more? So 512, 512, 512 here. What was missing in self-attention? Let's say if I don't use this feed-forward network, what was missing? Can anybody remind me what happened in neural networks? What was every hidden layer doing? What was every hidden layer doing in feed-forward neural networks? You compute Z, which is the linear part. You compute Z, which is the linear part. Then you compute non-linearity. Okay. Have you seen any non-linearity anywhere in this, or we have seen just matrix multiplications? Right. So apart from softmax, everything here was just linear. So what transformer architecture, what the authors comment say, this is mostly a linear layer only, apart from doing softmax. Now let's say, if you don't have this feed forward here again, so this was our encoder block. So if output of this, if we let's say stack one more self attention on top of it, then that is not going to do anything different. That will simply going to rearrange the weights on different units, right? Because there is no, remember what is the argument we gave for this, that if your hidden layers, if they don't compute non-linearity, what do you lose? Right? So then we saw that if you don't have non-linearity in the hidden layers, you better don't have them, because it's just a matrix multiplication that you can do. So you don't need 3 matrix W, K. So basically everybody knows that, I am not going to repeat that. Okay. So this feed forward neural network, here you have this whole layer just to take care of non-linearity. Okay. So So this is just to compute the nonlinear representation of attention outputs. So now, how should this layer be how should this layer look like? अच्छा, we missed one class. When shall I make it? आज कर सकते हो? Second.
फर्स्ट हाफ में आप 2 घंटे स्ट्रेट कीजिए सर, मतलब फिर वो ब्रेक नहीं होगा ना सर.
9 to 11 is okay? नहीं, 9 to 11 tomorrow not possible for me. Anyway, coming back to this. So how should this layer look like? So 512 inputs here, what now? You know what was the mistake I was doing in that matrix multiplication? So I kind of had it at the back of my mind that resulting vector will be 64 cross 1. And that was messing up whole thing. So thank you for pointing that out, and thank you everyone for everything. Next. Yes. What should this do? This takes input of size 512, gives output of size 512. How should my matrices here look like? So we have expanded this part now. Okay. Now we are going to expand what lies here. So let us go back there. Now, so these are the 512 size inputs. What shall I call this one now? First, so let us call this as Z1, Z2. Why Z1, Z2 and why not V1, V2? Because these are not V1, V2, rather concatenation of 8, V1 from first head concatenated with V2 of the second and so on, right? So that's why they are Z1. Nice. Now, what do I do here? What should come here? And my output here is again 512, 512 and finally 512. Yes.
एक्टिवेशन फंक्शन
Hmm?
सर वेट के साथ मल्टीप्लाई करके फिर एक्टिवेशन फंक्शन
So how do I do this? Take a input of size 512 and give output of size 512.
सर इसमें लर्न क्या करना पैरामीटर्स का सब सर इनपुट लेयर आउटपुट लेयर 512 512 बना दें
Okay, so let me try to make the network here now. So this network is what I am drawing here now. You said, Ashutosh? So 512 inputs. So my input layer has 512 neurons. Okay. What more? I mean, output layer also has 512. What more? Hidden layer. So give me the size of hidden layer now. So for this dimension I have to go and look at the paper, what are they exactly taking. Right, so they take this to be 2048. Okay. So see here first. So 512 inputs, 512 outputs, and your only one hidden layer, so not much complicated things out there, and that is 2048. Yes. Now, is this necessary for this guy to have 2048? No, right? So even if I am wrong here, this was not 2048 in original transformer paper, right? This can be some other number. We will see in GPTs, in BERT, these numbers actually change. So I don't remember for any of them. We will see in BERT, GPT, even these numbers will change. So, but the idea is this: 512 size input, 512 size output, and then you take a projection here, okay, and that is it. So now you also, so you basically take ReLU here. And what are you going to take here? Can do the same, okay. Now this is fed to what? This is fed to next encoder, and who will take it? Encoder will take it, but in encoder who will process it now? Self attention again. And you keep on repeating this for 6 encoders. Okay. Why we don't see any word embeddings here? Word embeddings were involved in the first layer, first encoder layer. Why are they not here? Soft. So I don't get this next after.
सर यहाँ पे तो सर वर्ड एम्बेडिंग्स इसलिए नहीं आई ना क्योंकि सर मतलब जो सेल्फ अटेंशन हमने यूज किया था
Right.
तो सर जो हमारा इनपुट है उसमें सर वर्ड एम्बेडिंग्स की जगह अब की बार अटेंशन आ रहा है कि मतलब वर्ड एम्बेडिंग्स
Right. And
वर्ड एम्बेडिंग्स को बार-बार अपडेट नहीं कर सकते अपन।
so see, the job of word embeddings is over. They were used at the very first time. Now these representations that you are having, okay, these representations, the claim is that these are much better representations of, see, in the end what are you doing? In the end you gave input as x1, that became z1, that finally became something else and was fed to next encoder. What is this whole thing doing? This stacking of encoders. This is just representing words. So this is just improving the word representation of each word. So you started with word embeddings and then now you are incorporating more and more contextual information into that. Okay. So you keep on passing this to encoders and then we are done. Okay, so I have a couple of questions and a couple of things to say. So we come to here. So which boxes we are done with? Multi-head attention is fully done, nothing is left. Feed forward is fully done, nothing is left. But there is something in between that I am going to do. So you know, this connection is called a residual connection. I will not do this in the class. I will give you reference to a few videos of mine. Go through that and then we will talk about this. So I will not take residual attention, residual blocks in this class. Okay. Add and so layered normalization is something I will take. So then we are more or less done with this encoder part, except one thing. What is that? So see, do you see that each and every word is being okay. This was for x1. What should be for this guy? And similarly for all these 512. So this network was there for this first unit. What should be the network for second unit? Same network? By same network right now I mean a network of the same size. But what do you think? Weights will be shared or it will be a different parameter matrix altogether? How many of you go for different? Same? Same? How many of you go for same? Different? There is no right and wrong. Okay. What transformer paper does, see, ideally you think of it this way. There are computational issues otherwise. Think of it this way, if you keep it different and if the best way is to keep them same, network should be able to learn these parameters such that they are same. But right now these kind of things are not happening. Okay, network starts behaving in a very weird way. So what you actually do is all these weights, they are shared. Every word is passing through the same network. Okay, so all weights are shared. Effectively there is just one matrix, but every word is being passed through that matrix. So for first word, this same network will receive word Z1, process it, give output. The same network the same parameters will be used for this one. Tell me how many things can I do in parallel here?
पैरेलल में कुछ नहीं हो पाएगा, एक बार भी एक ही जा पाएगा अगर अपन सेम ले रहे हैं तो Z1 जाएगा, Z2 जाएगा।
Any other opinions?
अगर अपन शेयर्ड पैरामीटर्स
Other opinions? See, we started this mess saying what? We want to use GPUs, we want to parallelize everything, and now if you are saying I should do Z1 first, Z2 next, then what was so wrong with LSTMs? Okay? So, every word is taken care of independently. Do you see any connection of this pipeline with this pipeline here? We have not connected them in any manner except one, which is no, at which place? See, if you make them completely parallel, what is this? This is stupidity. Okay? If you make, there is a sequence of words, you process every word independently all the way until up there. You are not processing a sentence, you are just processing words. So they must be connected somewhere. Which thing connects them? It is the self-attention that connects them, because it is asking everyone, how much should I depend on you? So in that sense, self-attention is that part which is taking care of making it as a kind of, a one word being dependent on some other word. All these lines are happening in parallel. All 8 heads are working in parallel. Since you are at Google, you can do all these things in parallel. Okay? We can't even do just single thing here, because you see the parameter matrices size now. So if you are processing everything in parallel, where is the sequence property of sequences? Which property makes sure that x1 came before x2, x2 came before x3 and so on? It was natural in LSTMs. You will process x1 first. Once you are done, you will process x2. So by the structure of LSTMs or RNNs, it was natural. It was embedded there. Here, what do you see that can be said as that they are, capturing the essence of a sequence? That is x1. So x2 will follow after x1 and x3 will follow after x2. Which is the thing that takes care of this dependence, this property? If you don't take care of this, what will happen? Everything will fall apart, because this 512, so you are just processing 512 bag of words in parallel, because you take any permutation of this, your processing is going to be the same. See, if every line is parallelizable, right, you take random permutations, and will computation still remain the same? Think over it. See, I am doing a computation here. How does it differ if I were doing it there? Because the numbers are same. So any random permutation of this is going to give you the same computations. You need to bring in back what? The notion of sequence. But if you start keeping this kind of thing, that Z1 will be processed and then Z2 will be processed. After that, Z3 will be processed. This does not make sense. What do you do? If you see here, so have a look at here, before you start with the first encoder, this is your input embedding, you also feed something called positional encoding that encodes the position of the words that we are going to give input. This is something we will talk about in the next class, and I hope I will also be able to do add and norm in the next class. That should complete this whole thing. Okay, that's it for today's class.